All right, 3, 5, free fall motion, or actually your notes say uniformly accelerated motions, objects falling freely to Earth. And for the worksheet, just do number 1B, then number 2 and number 4. You could do 1A if you wanted to. If you do 1B first, that's the main one. 1B is slightly different than what I'll be talking about here. Like it might be not exactly like an example I'll work out for you. All right. Oh, this chalkboard is getting very dusty. Okay. All right. Anyway, for the free-falling motion, what we're talking about is objects that are falling under the influence of gravity. This is 3, 5. And all of the equations that I've been giving you before, all the kinematics equations, like for example, you've seen this one. Delta x equals VOT plus 1/2 AT squared. And the other one I like a lot, I told you V final squared, V initial squared plus 2A delta x. And of course acceleration, final velocity minus initial over time. These equations can be altered a little bit when you're talking about vertical motion, when things are falling under the influence of gravity. Now, anytime, remember we talked about Vox VAT before. V-O-X, V-A-T, V-X, V-A-T, 5 things. And I told you, if you knew any 2 of those, then you can find, if you know any 3 of those, you can always find the other 2 by using the 5 equations. I don't have them all written up here now, but I've got, well, I could put that off the other one too. Average velocity. And then it also could be V initial, V final over 2. Under constant accelerated motion, these are the 5 equations that we use, the 5 kinematics equations right there. Okay. And I know it's a little bit weird on the video there. I'll try to bend that up a little bit. That actually helps a little bit for a second. Okay, now, if you know any 3, you can always find the other 2. Well, when you're talking about an object falling under the influence of gravity, we know that the acceleration of an object due to gravity is equal to 9.8, usually 9.81 meter per second squared. That is acceleration g due to gravity. Or the way it's really written is with the letter G instead. G takes the place of A. But we know acceleration. So for all of these, we know acceleration. That means we only need like maybe 2 more things to be able to figure out all the others. All right. Now, let me see. So what you can do, if you wanted to, a lot of times the textbooks will do this. Delta X is like horizontal displacement. So if you're going vertical, we just call it delta Y. Is V initial times time, A, and then you might, instead of A, you might put a GT squared. You know what? I don't really even worry about it. I keep the same equations, and just remember, if it's going vertically, delta X is really delta Y. You'll see me, sometimes I'll put a delta Y in it, and I know acceleration is gravity. And by the way, gravity's acceleration is always negative. If you're going to let down be negative, which I usually do that. Usually up is positive, down is negative, and negatively negative 9.81 meter per second squared. It's almost 10 meter per second. It's about 10. So what does that mean? If you stand on the highest building and you drop an object off, like Empire State Building, if you stand there and you drop something, it will be accelerating at 10 meters per second per second. What that means is, you start off, you drop it. It starts off at 0 before you drop it. That's the initial velocity. Then after 1 second, it'll be going 10 meters per second. As it falls in 1 second, it'll be going 10. After 2 seconds, it'll be going 20. After 3, it'll be going 30, then 40, and so forth. So every second, it will go faster and faster and faster. The neat thing is, though, when it falls, like in the first second, it might fall this far, the second this far, the third second this far, the fourth, as it falls down, it's going faster and faster. So every second, it's traveling more and more distance. It's constantly increasing. You know, you might say slow, short line, longer line, longer line, longer, and on and on. So that's why you don't want to jump off of something that's too high, because You know, you can jump a few feet down, a few stairs, but any higher it starts to hurt pretty bad because you're going faster and faster and faster, constantly accelerating as you go down. Okay, well, so yeah, on the notes there I wrote the delta x. I changed it to delta y if you want to use that. Okay, here are a few interesting little things. I wrote 3 points there. Number one, all right, watch, I'll show you this. Wow, this is so dusty. Chalk. Okay, if I throw this up, I don't have very much height. I'll go off the video screen. But if I throw it up in the air and then back down, up and back down. Oh, okay, well, tried. At the highest point, we know something is true. At the highest point, the velocity of the object will be 0. So if you throw a ball or anything up into the air as high as you can, at some height, as it goes upward, remember the accelerating gravity is pulling it down. So it's actually accelerating down. What that means is it's slowing down. As it goes upward, it's slowing down at negative 9.81 meter per second. It's slowing down. So as you throw an object up, it's getting slower, 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 slower. Then at the highest point, its velocity is 0. Then, as it falls back down, it's going faster, 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 faster. Okay, so that's the first thing. Number 2, I wrote V final is equal to negative V initial. Let me tell you what that means. And sometimes I'll draw a diagram, or other people will do this to show you. So let's just say you throw something up in the air and it comes back down. Now, you might not make a loop like that, but we'll just pretend. If it went straight up and down, it's easier to draw the picture this way. So let's just say you threw it up. You're going up here. Here's the highest point. At the highest point, the velocity we know equals 0. It went to 0. So let's just say you threw it up in the air, and then it comes down right there. So you went up, went to 0, and then came back down. When it left your hand, let's just make up a number like, let's just say 7. Let's just say that when it left your hand, the initial velocity, VO, is, we'll say, positive 7 meters per second. It's going that way. When it leaves your hand right there, it's going positive 7. So it goes 7 and slowing down, 6, 5, 4, 3, 2, 1, 0. At that point, it's 0. Then it falls back down. 1, 2, 3, 4, 5, 6. And guess what? 7. Now, the final velocity will equal also 7, but now it'll be negative, just meaning it's coming downward in the other direction. So when it leaves an object up, so if you throw an object and it goes up, comes back to the exact same height where it left your hand. When it left your hand, it had, just say, if it were going 5 miles per hour when it left your hand, it's going 0 up here. When it gets back down to your hand, it's going to be going, we'll say, hitting you with negative 5 miles per hour. It's going the same speed, but it's going the opposite direction. So that little rule number 1 said at the highest peak or highest point, velocity is going to be 0. You can call that we'll talk about that later. At number 2, at the initial velocity and the final velocity are equal, but they're opposite in direction at the same height. So the velocity here and there are the same, up and down. And then third, it said, well, yeah, I already told you this, but the object is accelerating negative 9.81 meter per second squared during the entire time of travel. So like I said, as it goes up, it's accelerating, meaning it's slowing down. In this case, negative 9.81, slower, 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 0. Then it comes down, negative, negative, negative. You're going faster and faster because you're going in the negative direction. Okay, all right. So let's try letter A here. And these are fun to work, and boy, they're amazing to do in real life too, to do these little experiments. I'll come back to these equations in a minute as we need them. I'll just show them to you. But you should always have them in front of you next to all 5 of those equations. All right. Letter A says this. A penny is dropped from a tree. A penny dropped from a tree strikes the ground in 2.71 seconds. What is the height of the tree? How about that? You can even go on the side of like a cliff or mountain or whatever. You could drop a little a brick or a rock. Don't drop. Make sure nobody's down there. But drop a rock, and then listen. Start timing right when you start. You drop. Start your stopwatch right when you do it. Let go. Boom. Right when you hear the click, the boom when it hits the ground, stop your stopwatch. If you know how much time it took to fall, you'll be able to figure out how tall it is. Okay, that's what this problem is. That's a neat thing. Now, of course, if there's a lot of wind, it could slightly affect, probably not much, because especially the wind is most likely going to be going horizontal. It's not going to go up or down or anything. So, okay, so it strikes the ground 2.71 seconds. What's the height of the tree? All right, the first thing there, it might look like you're not given a lot of information here, but remember I told you for Vox Vat, for free falling, you already know acceleration. You just need to know two more things. So we know the time. We know acceleration is 9.81. We know the time it took. They gave you that was 2.71 seconds. And we know one more thing as well. What do we know? We know the initial velocity. Okay? This is an important word in this physics problem. When you drop an object, the original velocity was 0, okay? The initial velocity, I shouldn't say original, it was 0. Now, if you threw it downward, it wouldn't be 0, but you'd have to know how fast you're throwing it down, then you'd know the initial. So we know initial velocity, acceleration, and time. So look at what we can find. You can find the final velocity, actually. I didn't even ask that in this question, but that's why it's good to have a little Vox Vat. We can find the final velocity, and we can also find the height. To find final velocity, let's just go on and find that, even though they didn't ask for it. Well, you don't even really need it. Let's not do it yet. Let's just do the question. I'm sorry. All right, let's find out what is the height. This is the equation I'll use. And if you want to make it delta y, you could. The height, delta y, will be initial velocity times time plus 1/2 at squared. Now, on a problem like this, it's okay to use that equation. I said that I try to stay away from it a lot, but here I'll do it because the initial velocity is 0. 0 meters per second. The time is 2.71 seconds plus 1/2. Now, the acceleration is negative 9.81 meter per second squared. And the time, again, is 2.71 seconds, and it has to be squared. So, when you put that in, you see you get that. That's just going to be 0. So, 1/2 times that, 9.81 times 2.71. That's 26.5. Then divide by 2. Up! No, Vela, I forgot. Messed up. See, bad Vela. Bad Vela. Square that. 2.71 squared. Yeah, I guess I'll take an extra step. So that's going to be 7.34 times 9.81 times 1/2. And, okay, now let's do it. So I forgot to square that. So let's do that. 9.81 times 7.34 times, or divide by 2. 36. Negative 36.0 is the answer. Now, let's think about that for a minute. The question says, what is the height of the tree? That's a tall tree, 36.0. It says negative 36. Is that true? Well, the height would be 36, positive 36. Think about this for a moment. You dropped an object. What you found out was, as you dropped the penny, you found out the delta x, or delta y, we'll say, the displacement. You found out what was the change in position. The change in position of the penny was the penny went 36 meters lower. It traveled 36 meters negative. So that means the height was positive 36. So that's a little drawback to that. You've got to remember that negative in this problem, it's not that big of a deal. Negative is the penny's displacement, but the height of the tree is 36. So don't worry about that negative there. Now, if you wanted to find, and let me just do that. If you wanted to find what is the final velocity as the penny struck the ground, what was its velocity? Well, then you could actually just go on and use the acceleration equation. That's actually very easy to do. In fact, the way I told you before, you might do this first and then use a different equation. But that equation, when you're dropping an object, that's a pretty good equation to use. I showed you there. But otherwise, you can use this other one. So, all right, we know acceleration is negative 9.81. we know that the final velocity, we don't know the final velocity. We know the initial was 0. And we know the time was, what was it, 2.71. 2.71 seconds. Okay, so just do the algebra here. 9.81 times 2.71 is 26.5. Equals the final. That's it. Just multiply those. Now, it'll be a negative number, 26.5 meters per second. And that makes sense that it's negative, again, because the penny was going downward. They did not ask you to do this on the question. I just wanted to show you. You could remember with the Vox VAT, we know initial was 0, we knew gravity, and we know time was 2.71. So we can find the other two things. So, and that V is a V final. Just kind of remember. If you're not, I'll probably mention it to you in the lesson, but if you're kind of unsure about this, you might go back and watch the lesson of that came before this on the Kinematics Equations. There were actually 2 lessons on it. But I'll probably also go over it in the lesson in class. Okay, now let's look at B. And I know sometimes I'll give you some pretty strange problems in here. It says, a television is thrown upward to a height of 8.45 meters and is then caught at its initial position. Okay, so what they're saying is kind of like the diagram I showed you. You threw a television. Maybe you got a friend that's, you're like, I don't want to walk up the stairs. I'm just going to throw this up. 8 meters, that's pretty, well, could that be a whole floor? I'm trying to think about that. That could be, it could be like an apartment or something like that. Hey, going to throw it up to the 2nd floor. You're going to throw I'm just going to throw it up there. I don't want to, good Amazon delivery, whatever. So, I don't know if they ever do that. But if they throw the TV up to you, but apparently somebody missed it, and so it came back down, but the guy caught it, because that's good. So we threw it up in the air. It came back down. It wasn't supposed to come back down, but oh well. At least it was caught and not broken. So it was thrown up into the air to a height of 8.45 meters. So now we know this is 8.45 meters, which is delta x, or the height, the distance, or delta y. If you want to call it delta y, it's probably better because it's your vertical delta y. 8.45 meters is the height. So back to the little Vox VAT, we know delta x now. And we also know a. We always know the acceleration. And it was at the time they gave you also. It said, no, it didn't give you the time. Okay. And, okay, here's an interesting one. So, find the time of travel and the final velocity of the television. So now it looks a little tougher. Like, wait a minute, what can we find? We only have 2 things given there. We only have the height and we have the acceleration negative 9.81. But what about the others? Well, it turns out there is something else that we know. Remember I told you, when you throw this up in the air, at the highest point, we know the velocity is equal to 0. So let me get another color chalk. Oh, wow. I have this poor chalk down here. It fell on the floor and it's been stepped on and crunched and abused and all this, but oh well. I'll try to do it with the yellow. All right, so at the highest point, I'm going to keep my drawing there. At the highest point right there, we know the velocity is 0. And also we know that it traveled downward, not too good there, 8.45 meters. So we could imagine a problem and just say, let's just imagine that you started right here at a velocity of 0. And you just dropped it straight down and it went down here. And obviously it's not going to be 0 when it strikes. We don't know the final velocity, but we do know that it went 8.45 meters. And look at this. So we're only going to take half the problem for a moment. Let's just talk about the half where it came down. As it came down, it started up here. It started here at 0. It fell this distance, 8.45, and it ended with this final velocity. And the whole time it had the acceleration of negative 9.81. And the initial velocity was 0. So we're only going to take half. Now what we're going to be able to figure out, we'll be able to figure out the final velocity that it has down here. Is that one of the questions? It is. That's actually question B. B has A and B, and part B we're going to find first. What was the final velocity of the television when it struck down here? So we can just do half the problem and figure that out. So we know final, the time, and we know the initial. So that turns out to be the equation that I like a lot. V final squared, V initial squared plus 2A delta x. Or in this case, we could say delta y. I'll put delta y. Wow. The chalk, the chalk. Okay, so here we go. So final we don't know, but we know that the initial is 0. Isn't that great? It's great. It's fun to put 0 in numbers on the equations because that's going to be easy to work. Times 2. Now A is gravity, negative 9.81 meter per second squared, and delta y is 8.45. Now actually, since you're going up and coming down, it's actually negative 8.45. That way your number will be positive anyway, meters. Okay, so V final squared equals 9.81 times 8.45 times 2, 165. By the way, I'll just tell you this too. When you're doing a problem like this, I assume that up will be positive and down will be negative. If you wanted to flip it around and say, well, let down be positive and let up be negative, then you could, in that case, it'd be positive 9.81 and positive 8.45. So you kind of could eliminate the negative sign. So in other words, you could just put that and it would still be correct. I like to kind of keep it consistent and put the negative in the negative. But if you're doing a problem like this and you see like square root of negative, obviously you know if you forget one of these, if you forget to put a negative in there and you get V final squared is negative 165, you think, well, I can't find the square root of a negative number. Well, you know, you can just erase it and find the square root. You're going to get the answer. But technically, you might want to see why is that negative there, and hopefully you'll remember, oh yeah, they both have to be negative, okay? Or they can both be positive. Okay, talking about all this stuff, because you might see it. And now that I look closely, it's really more like 166, but oh well, because 165.7. So get the square root, and it's the square root of this side equals the square of this side. So V final is 12.9 meter per second. So it tells me a couple of things. First, it tells me your final velocity, really, you should say the final velocity is negative 12.9 because you're coming down. But that depends on how the problem was. I wouldn't care about that. So on this problem, on a quiz or homework or whatever, negative 12.9 or 12.9 would both be okay. It wouldn't matter on this one. Now, the other question, letter A, was what was the time of travel? What that meant is you threw it up into the air, went up, came back down. Okay, well, it turns out we can keep our little idea about the half side and it still works. Because here's something else that's also interesting. It should make perfect sense. If it took you 2 seconds to go up, guess what? It's going to take 2 seconds to go back down. So if I figure out the time for the half trip, just from there falling back down, and I double that number, that will give me the total time of travel. So what I'll do is I'll use the equation that is pretty easy. V acceleration equals V final minus V initial over time. Remember I told you, you always want to try to use that equation. That one and the one I used a moment ago are my two favorite equations. Always try those out, okay? V final squared, V initial squared. If not, then go to this one. It turns out you couldn't have done this without doing the other one first. Now you can do it another way, but I'll do this instead. So again, acceleration is negative 9.81. V final, we just found it was, oh my goodness, can you believe I didn't write it down and I don't remember what it was? 12.1, right? Was it 12.1? Oh boy. Well, I think it was 12.1. If it wasn't, then I'm sorry, but I can't run back my video to see. 12.1 meters per second negative. If it was something else, then put in the number there. I think it was 12 something. Minus the initial velocity is 0 for the half trip. You know, for the half trip, I'll call it the half trip, just the falling down part. Initially was 0. Final was negative 12.1. And the time of travel, oh my goodness, this is so bad. I didn't write any of this down. What was the time of travel? Oh, we're trying to find the time of travel. Okay, we got everything else. Okay, bad, crazy fellow. All right, yay. Okay, I'm going to be okay. All right, now, the math looks pretty easy, but the t goes on this side, so negative 9.81. Sometimes I'll write the t like this, like with a little loop hook on the end of it, like they do on that little font. That way you don't think it's a plus sign or something, but oh well. I didn't do too good there, but negative 9.81t equals negative 12.1. So now divide both sides by negative 9.81. And your time equals 12.1 divided by 9.81. 1.23 seconds. But now, that number is only half the time. That's the time it took to fall from the top back down. So as I told you, the time to fall down will equal the time to go up. So the total time of travel. Now, sometimes in football too, they'll say hang time, okay? Or you might hear, they don't say that too much, do they? But hang time would be like, how long is it in the air? So when you kick the ball off, I mean, of course you want to go as far as you can in football. But also, you think about sometimes you want to go real high, and sometimes you don't want to go real high. If it goes really, really high up, it gives you a lot of time to run down there, depending on the time on the clock and all. Sometimes you want to kick it lower. So hang time, that's what we mean by here. The total time will be the total time in the air. It left, the TV left the hands there, in the air, in the air, in the air, in the air, slowing down, stopped. In the air, falling back down, down. Okay. That total time will be 1.23 times 2, which will be 2.46 seconds. All right. So as I said, just do number 1B, number 2, and number 4. And that'll be all. See you guys later.